you haven't been around in the Institute for some time, I'm David Wallace. I'm the director of the Institute. I'm just here to say a few words, mainly of welcome to all of you. I hope that you have a great time this week and that it's an interesting and stimulating time, and that you enjoy the ambiance of the Institute. Just a few other things. Firstly, if you have any issues or questions or you need any help, please don't hesitate to ask. The staff are here. The purpose of the staff is to help you to make your time here as efficient and pleasant as possible. So if you have any issues or questions, please don't hesitate to ask the staff. The second thing I want to say is really to thank the organizers of the whole program. That's Ilya and Jan and Tom and Martin. They've done a great job, and I'm really grateful to them, because without people like you, we wouldn't be able to run programs at all. It's quite a bit of work, and I'm very grateful to you. The final thing is, and I'm looking and my eyes can't, here is Martin. I just want to say, I don't know whether this is common knowledge or not, but Martin Jungpower has just been awarded the Leibniz Award in Germany. This is fantastic because it gives him personally €2.5 million to support his personal research over the next 7 years. It's incredibly prestigious, and we're really pleased that, in a sense, Martin, you were here. We sort of bask in the reflected glory of this award for Martin. I'm afraid you're exploiting you as well. It's fantastic, and Martin might say, but what actually pleases me more is when we were having a little glass of champagne to celebrate. He mentioned that some of the citation relates to work in collaboration with physicists, which started at a Newton Institute about 10 years ago. Mathematicians. Excuse me. But the interesting thing about this, of course, is you never know how long these things take to come to fruition. So that's a great example. Anyway, thank you all for coming, and thank you again to the organizers, and enjoy, and I'm going to sit in on Tom's talk. So over to you.
Okay. Everybody already knows. This is the final conference of this program, and I only wanted to say that the idea was not only to have localization in this conference, but rather to deviate into different directions, which most of the time have to do with random media, physics of random media. One could call this conference equally well in this way. And this is the reason why we have different topics in the conference, in particular random walks in random environments, some linear stuff concerned with random environments, and things like that. Okay, now I would like to announce the first talk, and I would like to say 2 words about the timing of each talk. So we usually have 50 minutes per talk and 10 minutes for discussion. So I would like to ask everybody to try to keep to this. To these restrictions, I mean, to follow these restrictions. And so Tom promised actually to do that and to set an example. But probably more importantly is that he's going to say something interesting about quasi-diffusion in 3D, SUSY Hyperbolic Sigma model.
All right. Thank you, Ilya. Put this switch on here. Got it. So, as Ilya mentioned, this conference is about dynamics in random media, quantum dynamics and classical dynamics as well. And my talk today is really about, I would say, statistical mechanics, motivated by problems in quantum dynamics in random media. And as you can see, this is joint work with Margherita Di Sartori and Martin Zirnbauer. I would first of all like to say something about the word supersymmetry that appears in the title with the initials SUSY. I have already, in this first frame, I have already broken a cardinal rule explained to me by Jean Bourgain and some of my other mathematical colleagues. Never put supersymmetry in the title or an abstract because you won't have any audience. So, but this is, my excuse for doing that is, first of all, I would like to explain that supersymmetry has some real power, and there are mathematical things one can learn from it. And secondly, I would say that fortunately for this audience, the Grassmann variables, the anti-commuting variables, which are part of supersymmetry, will be integrated out, so they won't last for so long. And we'll see that the model, the supersymmetric sigma model, is in fact very closely related to random walk in a random environment. So here's the outline of the talk. First, the motivation, which is to study the evolution of a quantum particle in a random environment using statistical mechanics. And so this model that I will talk about today is motivated by trying to understand this problem. And one of the main conjectures that is still open and seems to be very resistant to mathematical analysis is quantum diffusion for 3D random Schrödinger. We still have a very primitive understanding of this at a mathematical level, although I think and almost any physicist you talk to will say this is been well known for many years, and it's and why do you have so much trouble establishing this? And that's another question. Now, there are, of course, many questions that physicists would like to understand with having to do with random Schrödinger transitions, for example, between localized and delocalized systems. What happens in 2 dimensions, which is a very rich area. I mostly talked about 3 dimensions. And here the, let's see, is this, which one of these is the, oh, maybe this does it. I'll use something else. So here we have this work of Franz Wegener, which I talk about in C, and then later Konstantin Efitov, who actually proved that spectral properties of random systems, many random quantum systems, are in fact equivalent to supersymmetric statistical mechanical model. And these models have an SU112 hyperbolic symmetry, which I will say something about today. And the spin in this model, if you like, or the field, is a 4x4 super matrix. And this is a fairly complicated model to understand. And so what we're doing really is to study a simpler model, which is motivated by perhaps attempts to understand models like this. And the main result that we have, that I'll discuss here, is to prove diffusion, the analog of quantum diffusion, only the analog, for a simpler supersymmetric hyperbolic model. And as I mentioned, excuse me, this is in fact equivalent, will be seen to be equivalent to a random walk in a random environment. And most of our work is to control this random environment, to describe the environment. Then I will say something about various algebraic identities related to supersymmetry, why supersymmetry is relevant for these problems, and why hyperbolicity enters. That's an important ingredient. I'll say a few things about the ideas of the proof. What's actually quite important are ward identities, which are identities coming from the symmetry of the system. It's important to have these identities for us. If we didn't use these identities and we were somehow not using them initially, then the problem would be, I think, much more difficult. So the Ward identities are absolutely key in our analysis. And then the rest of our analysis is very classical. It's random walk in a random environment, and your environment is not uniformly elliptic. So you have to worry about getting estimates on non-uniformly elliptic Green's functions, and that's a lot of what the analysis is about. Finally, to make contact with a couple of other talks here given by Franz Merkel and Sophie Rolls, I will talk about a little bit about the possible connection with edge-reinforced random walk. Now, this has nothing to do with quantum mechanics. It is a random walk. It's a history-dependent walk in which you tend to visit edges that you visited in the past. And this edge-reinforced walk, like our system, can also be written as random walk in a random environment. And then Alain Snittmann and Gadi Kozma had pointed out to me some time ago that what they were doing, what Merkel and Rolls were doing, looked a lot like what we do. And in fact, their environment, you'll see, looks a lot like our environment. So I'll come to that toward the end if I have time. So that is the outline. Here is just the framework for this kind of systems, of course, we'd like to study. And this would be random Schrödinger, where you have a potential which is random at every lattice site. And of course, this is widely studied in the mathematics literature, but something I think which deserves just as much attention are the random band matrices. And here you don't have deterministic you have random off-diagonal disorder. There's no deterministic part of this Hamiltonian. It's all random. And for that reason, these systems, I would think, and in some cases we can show, are easier to analyze than random Schrödinger. And one of the major conjectures, which I think is worth understanding mathematically, it's certainly well established in the physics literature, says that if the bandwidth, so this represents a band, that the matrices the matrix elements are concentrated in a band of width W. And if the bandwidth is much bigger than the size of the matrix, the square root of the size of the matrix, then we expect this matrix to have GUE statistics. And so this is, I think, one nice example of a problem which should be very amenable to supersymmetric methods. I will not talk about it, but I just mention it as an open conjecture. Okay, now in this frame, I want to just say basic things about quantum time evolution. We have a random potential or random band matrix, whichever you like. You can imagine other quantum systems. And here, let me see. Where is the? Is Steve here?
The laser.
Yeah,
On the back side.
On the back side. Yeah, let me see. Which?
This small one, this small one on the right.
On the right. And the back. Let me see. Maybe I have another one in my pocket. Yeah, this one. Here's my Swiss laser, so I'll use that. Yeah, that works. Okay. I know how this one works. Anyhow, we have a time evolution, and this H can be random Schrödinger or random band matrix. And one very basic property of the unitary evolution is that, of course, the L2 norm of this wave function is a constant as a function of time, so that probability is preserved. And then, of course, one way of measuring how this evolution behaves is to understand the spread of the wave packet. And this is usually done by the mean square displacement, which I put in x squared here, and I sum over x, and that tells me how much the wave propagates as a function of time. And there are finer descriptions of the time evolution, but for right now, this will be sufficient. You just look at r squared, which tells you how fast x squared grows as a function of time. And here are the main conjectures, which are very simple to formulate. In 3 dimensions, which is the case that I think many of us would like to understand better, r squared should grow like proportional to t. Okay? Now notice that in front of this, this coefficient d here, which is like a diffusion constant, will be proportional to lambda to the minus 2. So when lambda, which is the strength of the disorder, goes to 0, if lambda gets really small, this diffusion blows up. And in fact, if lambda were 0, r squared would grow like t squared. It would be ballistic motion. So once you put in a small amount of randomness, you will get, we believe, you will get diffusion, and you will get an r squared growing like t, just like a random walk in a random environment, for example, or just your ordinary simple random walk. So, so this is not something you can do, however. I want to point out that you shouldn't perturb about Laplacian, which is a very natural thing. Most mathematicians think, well, I just perturb about the Laplacian. But in a sense, that's incorrect, because the Laplacian would give you, just by itself, would give you just ballistic behavior. You'd see a t squared here rather than a t. Now, there's also the issue of classical diffusion. You can imagine that I have, let's suppose, I have a system of scatterers randomly placed. I'm drawing it here in the plane. And then I just scatter off this by bouncing off the scatterers. I can imagine these guys are hard scatterers, randomly placed. And you could call this classical scattering, or I could put a random potential in there and then just solve the Newton's equations in the presence of a random potential. And so what I'm discussing here is the quantum counterpart of that. If these scatterers are frozen and randomly placed, let's say with just hard reflection, this is understood only in one case that I know of. And that is the case in which these scatterers are periodically arrayed. And then we know from work of Bunimowicz and Sinai that this motion is, in fact, the classical motion looks like that of a random walk. So we do know that in 2 dimensions, this classical evolution looks like essentially a random walk, has a Brownian scaling limit. But one very important thing to say is that if I place them randomly, or even according to Sinai, if I move just a few of them around, and I ask, do I know that, can I describe the motion after a long time? The answer is, he does not know how to do it. And so classical evolution in random media and quantum evolution in random media are at about the same level of understanding. And my personal guess is that classical dynamics in random media is more difficult than the corresponding quantum counterpart. Certainly if I make these things not hard scatters but have some potential, and then I can have elliptic islands, it's a much more complicated problem. And my guess is that quantum diffusion, although still difficult, is probably simpler than this question. So we can discuss that afterwards if those people are interested. Now, the second main conjecture, which is open, is the fact that we believe, and I will show you some evidence for this in the model, that there is localization in 2 dimensions. That means that this trajectory really will somehow come back again and again, and there's some recurrence, and that means in terms of wave evolution that everything gets scattered back to you. Everything comes back. Of course, if lambda is small, this constant is absolutely enormous. It's exponential in 1 over lambda squared for something like random Schrodinger. So the localization length is enormous. And that's part of what makes it so difficult to establish. You will see diffusion for a long time scale, and then you should see this localization in which all the wave, it tries to move out, but it all comes back, ultimately comes back. So those are the two conjectures that we would like to address. And this model, which I will describe today, will say something about both of these issues, although we cannot prove anything about it in this case. So now I described the evolution in terms of solution to random Schrödinger, but there's a finer way of extracting information, and that is to use the quantum Green's function. And that means you just take your Hamiltonian, random Schrödinger, random band, subtract off an energy. This is the energy you want to understand. And I have to add an I epsilon. This epsilon will be quite important. And that's to make the inverse well-defined, of course, because my energy is typically inside the spectrum of this operator. And to get information about dynamics, you must square the Green's function and average it over the disorder. So this is the quantum diffusion conjecture, which I phrased in the previous frame, but now I'm saying it in terms of Green's function. And it just means that this Green's function should look like the Green's function of a Laplacian. And that, of course, in 3 dimensions would look for small epsilon like 1 over x minus y. So you would see quantum diffusion just means that I get a Laplace transform of the heat kernel, and that is, of course, 1 over x minus y. There's a small epsilon here, so that would actually be modified by some e to the minus square root of epsilon x minus y. But for very small epsilon, that's what you will see. And this d that sits down here is the diffusion constant, similar to the one I had before, but at a particular energy. And localization in this language means that the Green's function actually, instead of having a power law decay, will decay exponentially. And there's always this 1 over epsilon prefactor, which will appear there because as epsilon goes to 0, if I look on diagonal, this will be divergent because of the presence of eigenvalues near the energy E. So these are the two sort of signatures of localization, exponential decay, and power law. And of course, there should be, in 3 dimensions, there should be a transition, which is, as I mentioned, not very well understood. And now I will say something about supersymmetry here. And this is the simplest example of supersymmetry for those of you who haven't seen it. Right now, I'm not explaining where the supersymmetry comes from. I'm just writing down an identity for you. And I like to give this example because it's the simplest example of where you can see supersymmetries has some power, which maybe wouldn't be apparent in just studying, let's say we take an n by n Hermitian Gaussian matrix, which we know everything about. And we want to understand the density of states, which I denote by rho e. And this can be given as the trace of h minus e plus I epsilon. So this is an inverse of an n by n matrix. We average it over the Gaussian disorder and take its trace and divide by n. So this is a fairly complicated object in general. And what supersymmetry does is to rewrite this simple object in another fashion. It's a kind of Fourier transformation, if you like. And I will say something about it in the next frame. But here, I'll just write down the formula. So the formula tells us that the density of states here can be written as an integral in just 2 real variables, a and b. Nothing fancy, no Grassmann variables. They've been integrated out. And there are 2 advantages in this formula. The first one is, of course, it only involves 2 variables. And here we have many more. But that isn't the main thing to learn from this. The main thing to learn from it is look at the dependence of n in this expression. This n appears here, and it appears here, and here. It appears only as a parameter. And so it's very natural to go to the saddle point of this thing. So you have an integral in 2 variables. your saddle point actually occurs in the complex plane, so you must deform the integral. But by understanding the saddle point well and solving for the saddle point, you will see the Wigner semicircle law right away. And not only will you see the Wigner semicircle law, but you'll be able to control this expectation, which is not so simple, as epsilon becomes very, very tiny. Epsilon becomes of order 1 upon n. Okay? This is not so easy to do if you were just to work with method of moments or other methods. This gives you, this saddle point method has a lot of power in it. And this is part of the power of supersymmetry, that it enables you to see where the dominant weight of the integrals lie. So that's just an illustration. And here I will say what the key, something about the key supersymmetric identities without going into detail. And so this first slide here explains the main trick, which you all know is Gaussian integration. Okay? You take any n by n matrix, Hermitian. It doesn't have to be GUE. It can be any matrix you like. And now what's important is that I want to get a representation for this Green's function. I've set my energy equal to 0 here just so I don't have too many parameters floating around. So I want to get this Green's function here. And we all know that you can, if you look at, I have a jk element here, and if I integrate xj, xk, now x, you should think of this as just being a vector in complex, n-component complex vector, epsilon's positive. So if I do this integral, this is a Gaussian integral, you can compute it. You'll get the inverse of this matrix here, that's like the covariance, and you'll also pick up the determinant. Now you might pick up a determinant to the -1/2, but here, because we have complex values, we pick up a determinant to the -1 power. Okay? So now we have at least the Green's function, which we might want to work with, represented as an integral over x. And here we also have a determinant, which we don't want. And for this reason, and only this reason, we introduce Grassmann variables, because when we put those in and do the integration, we'll get a determinant to the plus power, and these two determinants cancel. So this is the basic idea, very simple, behind the supersymmetry. And so now I want to do one other thing, which is explain the hyperbolic symmetry, which is not apparent here. So this is also fairly straightforward to understand. You want to understand not just the average of the Green's function, but you need the modulus of the Green's function squared. So you need a complex conjugate. And so I have to introduce not only the x's, I introduce the x for one Green's function, and I introduce the y's for its complex conjugate. So here I've just taken the complex conjugate of the previous expression, and everything still makes sense. I want to just point out that the fact that this epsilon is positive, I've chosen my signs carefully here. Notice that the I times I is -1, and the epsilon is positive. So this integral is actually well defined. This h here is self-adjoint, but this rest of this integral is basically oscillatory. It's only after you average that it's going to become a reasonable expression. So the I makes the integral well defined. And here we have its complex conjugate. And since I've taken the complex conjugate, there's a minus sign that appears here. And there's instead of an x star, there's a minus y star. So that makes the difference. This taking of the complex conjugate gives you two different signs. It gives you an x, and it gives you an absolute x squared and an absolute y squared. And you can see that if you do this example in one dimension, well, not just one dimension, an n by n matrix where n is equal to 1, then h is just a real variable. It's just a real variable. And let me just make the average of h squared equal to a squared. Okay, so that's just a Gaussian variable, and I'll give it this variance, a squared. Now I want to do that. So if you use supersymmetry to do a very, very simple integral, which is a one-dimensional integral, This is the most complicated way that I know of writing a one-dimensional integral down. But it shows you what we do. This is actually what we do. So, except in a much more complicated context. So for this, for n equals 1, this is a useless calculation, but it will illustrate the symmetry. So if I do this calculation here, as I do, I have to introduce the x and the y. One x will give you one Green's function, which is one inverse, and the other will give you its complex conjugate. So here I have an IH x squared minus y squared, complex conjugate, and then of course I have a piece here which is convergent, and that comes from the epsilon. Okay? So this breaks, but you can already see the hyperbolic symmetry here. And if I average over H, which is one of the reasons we do all this work to begin with, so we can perform an average over the randomness, then you have x squared minus y squared squared, and all this oscillation has disappeared, and you're left, this piece of course remains and breaks the SU11 symmetry. But this is the origin, this is the basic origin of the hyperbolic symmetry, and although I've illustrated it for n equals 1, it's a general principle which is at work here. Yes?
Don't you pass this formula above? Where are the Grassmann appearing?
I have not put them in. I have only done the bosonic variables here. Okay, I have left them out. Worth pointing out, though. Okay, now we come to the statistical mechanics system I'm going to talk about. And this model is due to Martin Zirnbauer in 1991, and this model is expected to qualitatively reflect the phenomenon of localization and delocalization for random band matrices, random Schrödinger. It has all the phenomenology that you would expect to have, and we have only proved a little piece of it, but it's certainly expected to have all the phenomenology that we would like to understand, including a localization, delocalization transition. I would say you would not expect a quantitative agreement, so this qualitative is the best we can expect. And there's no direct mapping between any particular random matrix ensemble and this particular model we'll describe here. But you'll see this model is very rich and has a lot of structure. So here we have our spin, or your field, as you like. And this field belongs to a kind of supersymmetric hyperbolic plane. So think of S and T are just real variables, and they belong to a hyperboloid. Okay, so they belong, if you like, to the upper half plane or to a hyperboloid. And, but they're unconstrained. These are what are called horospherical coordinates, and they are unconstrained, and they lie in the reals. And the psi and psi bar are Grassmann variables, which you won't see for long, but they belong to this supersymmetric hyperbolic plane, and so these variables appear in the following way. The action, which I will write down after I get rid of these Grassmann fields, is quadratic in S. You won't see that because I will hide that from you. And it's quadratic in the psi bar fields. So we all know that if something is quadratic in a field, you can integrate it out, and you'll produce a determinant because there's basically a Gaussian integral that you have to do. And similarly with these quadratic fields, you can integrate them out explicitly, and you will form an effective action, which I call A of t. And since we've integrated these out, the only variable we're going to be left with is a real field t, which I've just noted A with this boldface t here. So it's a function of many variables on the lattice. This model can be formulated in any number of dimensions, and Martin actually solved this model in one dimension and in 1991, and established a localization in that case. So our new effective action, which I'll write down on the next frame, you'll see it's real, but because I've integrated out all these other fields, it's not convex and it's not local. You produced all kinds of determinants. So So now I can show you the model. Okay. We have plenty of time to discuss it, I see. So here's the effective action, and this operator here, D, is like a finite difference operator. And this let's suppose, let me do the following thing. The t's are real variables, and I'm going to make the betas. Usually we have a temperature, an inverse temperature, which is constant. But for the purpose of this talk, and to illustrate some of the symmetries that are present, I want to make the betas depending upon the nearest neighbor. You can imagine they're constant, but you could also imagine them to have a nearest neighbor dependence. And then I want to define a quadratic form or a differential operator given by the following expression. If beta is 1, if beta were 1 and the t's were 0, that would be my discrete Laplacian. That would be, and that would describe random walk on the lattice, with simple random walk on the lattice. So this is the generator for simple random walk in a random environment. Now the betas are random, they're not random, but they could vary. But what's really random are the t's. So every t configuration gives me a random walk in a random environment. And now it will describe the distribution, how you compute the distribution of the t's. And then the problem will be how these t's behave and how they affect the random walk. So here's the effective action. As I mentioned before, we've integrated out the s's and the psi's. So we only have one action. Okay, so here, this sum here is over nearest neighbors. And again, we have a sum over nearest neighbors. Beta here, I guess I should have put a beta ij in here too. I meant to do that. So there should be a beta ij in here as well as in here, okay, as I have it up here. So that's not important if you want beta to be constant, but I will make a comment about that in a minute. So our action consists of a nearest neighbor interaction with a cosh. This looks like a free field, actually. If you expand it, it looks like tj minus tj squared, but it has some anharmonic terms. It's a nice, this is a nice convex function. The difficulty and the interesting aspect of this interaction comes from the presence of this determinant. There's a determinant here, which is actually the determinant of this Laplacian, basically, in the random environment. So this determinant is extremely similar to the one that appears in work of Merkel and Rolls and also in earlier work of Diaconis. It's very, very closely related. And in fact, they have a determinant to the square root, just as we have. Okay? And this is the determinant of this matrix. Now, if t is equal to 0, let me just re-emphasize that then we're really looking at basically a Laplacian, especially if beta were constant. So it would just be the ordinary finite difference Laplacian. So this piece, however, because of the half that appears there, and it's a plus a half power, makes our action non-local, obviously, but is also, the action is not convex. Okay? There's a competition between these two guys, and they will produce possible phase transitions in the system. So here's how we define the expectation of a function. We just plug it in here, and notice I have a Jacobian here, which is not present in the weight, but this is an e to the minus tj. Tj is running from minus infinity to infinity, and what's important here, excuse me, is that so one of the first Ward identities, one of the first consequences of supersymmetry is the fact that the partition function is identically 1. It's 1. And the point I was trying to make here, and I see I didn't quite write it out properly, is that the beta ij that's present here can also be present here. And as long as I put the betas properly in here, this partition function is 1 no matter what value of beta ij I choose, provided the integral is well defined and the betas are positive. Okay. I could even add next to nearest neighbor interactions. This partition function remains at 1. I actually need to divide by some factors of 2 pi or square roots of 2 pi here, but modulo this is a correct statement. And so this is already a sign. This is already this observation, this fact that comes from supersymmetry is already one of the key tools that we use. So you could take, for example, the logarithm of the partition function and take a derivative with respect to beta, or some pair of lattice sites. You'll get 0, of course. Okay? So, or you could take several derivatives, or you could put in some longer range interaction and write your partition function down. Take the derivative with respect to that. You'll also get 0. So these are ward identities that come from supersymmetry, and they turn out to be very useful. They make up for the fact that we have a very non-convex and non-local action here. This action is real, it is positive, so it is statistical mechanics, but it's not of the standard type. So the ward identities are already implicit in the fact that we know this partition function is 1. And I believe from looking, and this is more speculation than, and maybe Franz Merkel or Silke Rolskup will comment on this, the fact that this partition function is 1 is, I believe, basically, for me, it's just, I would say, a reflection of not just the supersymmetry, but it has to do with conservation of probability. They have a similar partition function, which is not 1, but something they can compute explicitly. So there's very little difference between the two. So I believe it's just, all of it just is conservation of probability. So that remains to be seen whether it's purely supersymmetric or whether there are other ward identities are more general than that. I believe they're much more general. Okay, so now let me come to this, before I state the theorem, let me say what the observable is, and you can see a few things from this frame here. Here is the Green's function we'd like to average and take the square of it and compute it. Let's let it be random Schrödinger or random band matrix in some number of dimensions. And then this is only meant by analogy. It's not meant to be an equivalence. It's only an analogy with this model. This model is motivated by problems in quantum transport. So here it becomes this Green's function, this random walk in random environment, inverted. So it is an elliptic. It is this elliptic Green's function here. Let me just flash it up so you don't forget it. It's basically your Laplacian, an elliptic Laplacian. However, it's not uniformly elliptic because your t's can be very large or very small. And then we can write this, and we do write it in a slightly different way. It's your regular d, but I've conjugated it, or not conjugated, I've multiplied it by this e to the minus t. And when I do that, it doesn't look like random walk in a random environment anymore. It looks like a Laplacian plus a potential. But this is not your ordinary random potential by any means, because this combination is positive. So this potential is not your usual random potential. This guy is positive. And I've put in red here because it's quite important, the epsilon term, this regularization term that comes about. And this regularization term has this epsilon e to the minus t. You see it's also in the determinant. If you see the determinant here, it has the same factor, except that when we multiply by e to the minus t on both sides, this becomes this e to the t becomes e to the minus t. And so let me move along. But now the main point is that, and here is the power of the saddle point, which I explained for the for the GUE ensemble, density of states. The saddle point has the following structure. Okay? In one dimension, you think this is going to 0, and as epsilon goes to 0 for fixed t, it does go to 0. However, at the saddle point, this combination does not go to 0. It goes to of order 1 over beta. That means your saddle point moves with epsilon in such a way that this combination remains of order 1. or it's small, but it doesn't go to 0. And this is a signal for localization. It tells you that this inverse, it's not a proof, but it shows that this inverse should decay exponentially fast, because if I have a Laplacian plus, which is, if I have an expression of this kind, which is positive, plus a mass, which is generated by this, then I will get exponential decay. So in 2 dimensions, you also see the same phenomenon, which is that if you compute the saddle point in 2 dimensions, you will see that even as epsilon goes to 0, this combination produces a very, very tiny but positive expression even as epsilon goes to 0. And so the saddle point is telling you that this does not really want to go to 0, that it really favors t being negative in such a way that this combination does not go to 0. And now, of course, in 3 dimensions, t is apt to be 0. That's what you can check if beta is large. However, if you do beta small, you will also see that there should be localization in this very simple saddle point approximation. So the saddle point, of course, doesn't tell you everything because you have to control fluctuations, but it's an indication of what you might expect to see. So as I said, the saddle point should tell you that you have localization in 1, 2 dimensions and diffusion in 3. So that's the t equals 0. At t equals 0, of course, this object would be just your usual Laplacian, and you would see diffusion. And that is the main statement. Here's the main theorem that we have. If beta is large, then t wants to be 0. The probability of, so roughly speaking, the probability of we can show that e to the p times t, let's say plus or minus p times t at any site, is bounded by a constant uniformly in the volume, which tells you that the t's don't want to fluctuate very much. They don't want to get very large or very small, and that's basically enables us to prove that this Green's function, which is the one that I had on the previous slide, this Green's function behaves as if it were diffusion. So in other words, I can just take t equal to 0 here, put in I would get Laplacian plus this epsilon. This would be a bounded term, and I would see some kind of diffusion. I should ideally see x to the minus 1. Now, here is a problem which is the reason that we have the term quasi-diffusion in the title. Okay? We cannot actually establish diffusion. We have a weaker form of it. This is not even the proper form of the diffusion which we can prove. It's an average version of that, I would say. But let me just say what the obstruction to proving diffusion is. And the main obstruction is that we have control over the fields at any particular site. We know they don't get very large or very small because we have bounds on it. But we would like to know, and we do not know, that the set of sites on which the t's are uniformly bounded by some constant m percolates in the system. That it should have that it should form a fat set. If we really understood this, if we had this a result of this kind, maybe a little stronger version of it, then we would actually be able to establish the diffusion, the strict diffusion that we would like, and perhaps even a kind of central limit theorem, which should be present here. The other remark to make is this is a large beta result, of course in 3D, and we expect, but have not proved, that for small beta, localization should occur, which means this Green's function should actually decay exponentially fast. And of course, there's a localization. With that remark, you expect a localization, delocalization transition, and of course, we have nothing to say about that at this point. But this is the main statement, and the word quasi comes from the fact that we cannot rigorously establish this diffusion, but we only establish something which is almost as good, but not really, which has to do with bounds on the large fields in T. So it's really a large deviations estimate that we establish, but that is not sufficient to give us enough control over this Green's function that we would like to have. Okay, So here I will just very quickly, since my time is running out now, show you one of the simple Ward identities. I now have expressed it in terms of all the variables which I had mostly integrated out. But here we have the t's, the s's, the psi's, and I have an expression here. And if I raise this to a power m, an average, we can explicitly integrate out the s's and the psi's. We know this is 1. And this is basically the key identity that we use in combination with characteristic functions and so forth. And that's an illustration of the Ward identity I referred to earlier. So, so here I will just do one more, show you one more thing. After you integrate out the s's and the psi's and the s's, then what happens is that you get a Green's function here. You get something of the following kind. And we just need to control this Green's function. This Green's function looks like the Green's function for that Laplacian with the t's. It's the generator for the random walk in a random environment. And basically what you want to do is get estimates on that. And once you have good estimates on that, you will have good estimates on this Kosh, which will tell you, if you have good estimates on this, you will know that the T0 and TLs don't fluctuate very much. So you first have to show that differences don't fluctuate, and then longer distances and so forth, and then you need to do some induction. So let me just conclude with a few general comments. So quantum dynamics has motivated us to understand a supersymmetric hyperbolic model, which I've tried to describe. And in this model, we see that we really have to analyze something like a random walk in a random environment. This environment is not so simple to understand, but that's what we've been able to do to some extent in 3 dimensions and establish some kind of diffusion. There's a saddle analysis, which I mentioned, and you can see all the phenomenology in the saddle, which is very nice. But of course, fluctuations have to be estimated, and this is what we did in 3D for large beta, and Martin did in 1D for the localization. Once the Ward identities are established, and these follow from supersymmetry, most of our analysis is very classical. It has to do with random walk in a random environment and understanding. There's some induction on length scales, but understanding these non-uniformly elliptic Green's functions. So there are, of course, 2 problems here: to establish localization in 2D and the transition in 3D, which is still open. And finally, to make contact with this work on edge reinforced walk, let me just say that it's it is very much like a random walk in a random environment, and this environment is not identical to ours, but it seems to be very closely related. As I understand it, the work that Merkel and Rolls have done in 1D and in 2D indicates a kind of localization phase. As far as I know, I don't know of any conjectures that say that the model has a localization delocalization transition as we expect ours to have in 3D. However, on the Cayley tree, P mantle has shown that there is a kind of transition from recurrent to transient, which has to be very closely related to the work that many of you know that people have done on the Cayley tree for localization. So, so now, what about this relation between? Finally, I just want to say one more word about relationship between quantum and classical dynamics. They're generally very different. However, there are a class of 2D quantum network models, and these have their origins in some early work, well, not that long ago, work of Gruersberg, Ludwig, and Reed, and then later Carty. And these models, these quantum network models, they're fairly special, but they're actually equivalent to percolation. So if you understand percolation exponents, which we do now in 2 dimensions, you can read off various exponents in these quantum network models. So in fact, I think there is probably there are probably special classes of models in which you really can make a very close contact between quantum and classical dynamics. Thank you very much.
So what is, maybe I missed it, the random walk you actually need
What does
to
it?
this, well, what is exactly the
Okay,
relation?
so let me go back. Let me see if we can have. Yeah. Okay. So every, as you all know, random walk, ordinary random walk, has a generator, which is Laplacian. In our case, the generator, think of beta as being constant now, is just given by this expression here. Okay? So it's just given by this expression. Now, if t's are all constants, then my walk is walking in the uniform environment. If my t's are fluctuate, then I'm really looking at the generator of random walk in a random environment. And if the t's, now intuitively, if the t's want to be very negative, then if you can think of this edge here as being a kind of local conductance, then if t's are very negative, your conductance is very small. If t's are very large, your conductance is very high. So you have random conductances on your lattice. Okay? And the distribution for these conductances is given by this weight. This very non-local weight. So I don't, it's not as if I have edges which are independent. Okay, I mean, that would be very nice if it were that simple. However, it's actually much more complicated and in a way much more interesting that these edges are highly correlated and that they fluctuate a lot. And the fluctuations are governed by this statistical weight. Okay. So it's random walk in a random environment. And this describes your environment. Okay? And what really, so how can localization occur? One usually imagines that localization cannot occur in random walk in a random environment. But in fact, it occurs because the t's want to take very tiny values in 1 dimension and 2 dimensions. And when they want to take very, very small values, you have very little classical conductance. Right? And if t's want to be of order 1, then of course it's just like ordinary random walk in a random environment, which is uniformly elliptic, and for which we have all kinds of central limit theorems. So the problem is to control the fluctuation of these guys, and that's what's basically done by controlling this expression. Okay? So you know it doesn't fluctuate very much, and it's of order 1. But in general, the t's can be quite negative, and that is the mechanism for localization. So this guy here, I probably should have spent a little bit more time discussing him. This is the one that, and our observables. Let me just show you. Our observable is expressed in terms of the Green's function of that. There's the Green's, there's the D, and you write it this way. And this, of course, after I do this, it doesn't look like random walk in a random environment anymore after I multiply by these e to the minus t's. It looks like a Laplacian plus a potential, right? But they're equivalent things, okay? This is obviously positive, this remains positive, and we hardly ever use this representation. We mostly use the fact that it's an elliptic operator of divergence form. Yeah?
Is there a picture like in the original reinforced random walk that you have a random walk with a memory effect, no?
Yeah, the memory you could say is actually lives in the determinant. It lives in this determinant. And in fact, in the edge reinforced random walk, which people study, they also have a determinant. It's almost identical to this. Okay? It is random walk in a random environment, and the determinant is nearly identical to this. Yeah.
Possible applications of your technique to the 2D model. Where does lie the main difficulty technically?
Okay. Well, as you can see in the 2D model, you can see the saddle point.
And the saddle point is very appealing because it's giving you the right mass, not exactly, but order ballpark, the right mass. Of course, the difficulty with this all saddle points is that you must eventually control fluctuations about them. Okay? And that's what we do in 2 dimensions. Well, 3 dimensions, sorry. 3 dimensions. But of course, in 2 dimensions, your fluctuations are going to be a little bit stronger. Right? So there's a fight between the saddle, which tells you want to localize, and the fluctuations, which we can't quite control. We have some control on fluctuations. We can show that things don't fluctuate for very long scales, but it's not enough to do this. So but I think this is one of the more, people ask, why should you expect localization in 2 dimensions? Well, I think this model, if one really understood it well, would give us some insight into this mechanism. But again, the problem is you have a saddle point, you have to control the fluctuations, and this we have not done.
So you need more information from word identities, for example.
Yeah, you need to use the word identities quite a bit. We haven't spent a lot of time. I think the first question we have to ask ourselves and solve is this question: how do you control it for small beta? But of course, a more ambitious question would be to control it for large beta in 2 dimensions.
Any other questions? Well, let's thank the speaker again, and we have